Well, good afternoon. Can everyone hear me and see my screen?
Yes.
Thank you, Jessica. Okay, let's see here. There is about 7 of us in here. Let's give some people a couple more minutes and then we'll get started. Okay, I'm going to go ahead and get started. There's about 9 of us in here, and I'll check to see if anybody else shows up, but I think that's good. So if you go to your home page, you'll see that I have a week 2. I want to make it clear that we're really not into week 2 yet. We're on Monday, but we are starting this a little early because this is a tough lesson. And I'm going to be right there with you the whole time. So as we go through this lesson and you feel like it's too much information, just remember we're going to spend some time on it to let ourselves absorb it. So it's the kind of lesson that you got to go through a couple times. It's calculations and it's really honestly hard. It's hard to teach. So, don't worry too much about it at first because we'll be working on it next week. So if you go to our syllabus, and I'm going to scroll all the way to the bottom, you can see where we're at. So we talked about heating with renewables, the basics of renewable energy, not renewables, but the basics of residentials and getting the idea of heating with renewables is what it was. Our lesson was called Residential Energy Basics. So the textbook's called Heating with Renewables. Space heating calculations is the next thing, and you'll see that we're going to be working on those next week as well. So I just want you to recognize where we're at. And Okay, so I'll go ahead and go back. So what we're going to start with is module 2, because we're going to be working on this on Wednesday. So Wednesday, we are on campus. Just to make sure I'm clear, we'll be on campus Wednesday at the Craig Porter Energy Center, which you should be able to find all that information in your announcements here on, let me double check that. Yeah, there's your address there if you don't know where it's at. Okay, but Wednesday will be the first, January 26th will be the first day that we're on class. And you're going to need probably some help with some of the stuff that we're learning about today. So before I get too far ahead of us, I want to take a look back at our e-textbook here and just identify a section that is on this week's homework to make sure that's clear. So if you were to go to the e-textbook that we looked at, you're going to, I'm going to scroll fast, so watch your eyes. You're going to have a question on your homework that comes out of this section. You've already covered this section, but you have a section where you're calculating some of these. So what you want to do is you'll look at that question and I'll tell you it's 11 cents. It's pretty easy. You just want to do 11 cents times 2.93 equals what? That's all the answer is really looking for. But that's back here in this. So you're going to have to, that's one of the harder questions. So this is just us learning how to calculate fuel. So we're learning the different costs of fuel, which is important when it comes to what type of energy system you're using. So if we're going to shift from one type of energy, such as electric, to natural gas, what is the benefit? And then you also have a question that covers the cost benefit ratio right here, where we talked about the house. It's very easy. So it's basically this example, but the example is just the numbers are changed. So you can show that you get the basics here, so you can determine a basic cost benefit ratio. So that is on your assignment 2, which is got both the chapter 2, which is what we're calling space heating, and some stuff from chapter 1. I didn't want to throw all that at you on your very first lesson. So is there any questions on that? Does that make sense? Okay. Let's get somebody else here. Okay. So let's go ahead. If there's no questions, you still have time to do your homework, of course. We click on our module link here. We can see that you have your YouTube ENRG page here. If you click on that, that'll take you to the YouTube page that will have the videos that we do together on there, and they'll be up there for the duration of the semester. You also can find the recordings in the Zoom link inside your Canvas shell over here under Zoom. But you'll also be able to see recordings on either YouTube or your Zoom page. All right, let me back up. Okay, so there's that. We're not going to go back through module 1. We've completed module 1. You just need to finish up your first homework. Some of you have already got started. That's due January 26th. You still can finish it if you don't get it done by that time. Those due dates are there to try to keep you on track. Okay, so just don't get behind. So try to get that done. Then when we look at module 2, because this is really off of week 2, you don't need to have your assignment 2 done by Wednesday or anything. It won't be due until January 31st. So we'll get started here shortly on this module and I'll have some questions for you and get you thinking about what we're going to talk about. And under module 3, you'll see you have your first project. This project is something that we definitely have to do together. So on Wednesday, we'll be looking at this as we're taking measurements of some of the rooms at the Energy Center and learning how to do our calculations. We have a spreadsheet here that will go with that. So I wouldn't worry about that just yet. You'll see a little bit more about what that is. I just have it open. So if you want to check it out, you can check it out. But I'm pretty sure you won't really understand it until we have gotten through this lesson. And we're possibly not going to get through all of it today. So if that's the case, I'll have to change our due date, but I think we can. It just depends. So let's go ahead and jump right in. So you'll see under our overview, you need to reference your e-textbook, your Energy Basics, which is the first one we had for week 1. And then what we're doing today is the e-textbook space heating calculations. And there is a PowerPoint that goes along with this. We're not going to go through the PowerPoint. We're going to go into the textbook itself because it's just very, very complicated. So that'll help us all stay on track as you're learning. There is some notes in here. I call it cost benefit ratio, fuel calculations, et cetera, et cetera. We have to see it for what it is. There's a bunch of stuff in there. So that'll be a resource that you'll want to reference. Then you see you got your assignment 2. That won't be due until next week. And then there are several links in here that we need to look at that are important to understanding how to do space heating calculations. Okay, so we're going to just jump right in here. I think I got it open over here already. And before we get into this, can somebody give me an idea, just so we can get a conversation going? If you lived or if you had a building and you needed to do a heating loss calculation, the idea is simply that you have a building that is going to lose heat through the walls in the wintertime or gain heat through the walls, the ceiling, the attic, the roof, the outside parts of the building. It's going to either lose heat in the winter or gain heat in the summer. We call that heat loss, heat gain. Now, what we want to take a look at is understand how could you possibly calculate that? So if I were to say right now it is 22 degrees outside, and inside the building it's 70 degrees, how many BTUs an hour do I have to make to replace the heat that I'm losing to the cold outside? In other words, to be able to calculate that, you have to think of several different things and understand several different things. So what is it that's going to keep our homes from losing heat? What's the most important thing? Does anybody know?
Is it just the walls and insulation?
Yeah. And so what do we have? We have a name for that insulation. When we rate insulation, what are we rating insulation in?
R value.
Correct. R value. So R value is really what we're looking at in a lot of this. So we've got to learn how to first look at a wall, an outside wall. So just to say it out loud right away, we don't care about the inside walls of the building. If I were to give you a diagram, and I am going to give you a diagram of a house, a single-story house, just to keep it simple for us, but you'll have one, and you're going to have to look at how to calculate the total heat loss, heat gain for that home at a certain temperature. And it's hard, but we've got a spreadsheet that's going to help us out. Okay, let's just put that out there. That's what our project one is. So the hard part of the calculations and stuff, that's just not going to be really a good thing that we do in our homework. You'll be struggling on your own. I think it would be something that's really good when we're in the computer lab on class on Wednesday, where I can answer your questions very directly and get you working on it. And then all of a sudden it'll start to click. So that's, you know, part of what we'll be able to do, but we'll be able to look at each building and we'll be able to look at the walls and calculate their R value. And once we calculate their R value, we have to add it together and come up with a calculation to where we know how many millions of BTUs we're losing an hour through that wall, or how many thousands of BTUs we're losing an hour through that wall. We really don't know. So does anybody know how we measure windows? Do we measure those in R value, or is there another value?
Would it be thermal conductivity?
Well, thermal conductivity is a way that we measure the value of anything. So that would include windows, but we'll jump into that a little bit more. I think I might want to take a step back and look at some of our links, because I think they're going to help. This stuff can get dry real fast, so we don't want it to get real dry on us. But windows are measured in U value, not R value, but we can convert U value to R value. So what we're going to have to learn how to do is look at a wall and go, there's a window space. How many square feet? What's the area of that window? What's the U value? Then convert that U value to an R value, then add that to the wall. Now, are our walls all made of the same material? What do we have inside our walls that we have to think about?
Insulation.
We got insulation, and that's one thing. What else?
Electrical cables, plumbing.
Sure. Actually, those are the things we kind of ignore. That's a good point, though. They are in the wall. Well, I'm thinking, like, what is a wall made of material-wise? Typically, we got insulation. What else is in the wall?
Like wood or drywall?
Yeah, we got drywall, or maybe wood paneling. You might even have a concrete wall, all concrete, or some fancy brick. You have different materials. You have insulation, and then we have 2x4 framing of some kind that's inside the wall. Then we may have plywood. We may have some type of barrier, like a Tyvek plastic barrier, or some polyurethane type foam. Maybe vinyl siding, maybe rock siding, fake rock siding, who knows? But each one of those actually has an R value. And as you can hear right now, it's like, oh boy, this starts sounding complicated. Well, it is. And the truth is you can't get the numbers exact, but you can get them pretty close if you do, well, if you learn how to use this spreadsheet is really what you're going to do. You're going to cheat a little bit. To do this stuff longhand on is pretty hard. So we're just going to learn how to use a spreadsheet, but we need to understand why we're doing the spreadsheet to begin with. Let me see here. I'm going to back out of this and go into our modules. Peter brought up thermal conductivity. I want to click on this link here, thermal conductivity. So at some point, we will need to find what the thermal conductivity is, and this is in BTUs right here, of any material. So if we were wanting to know brick, we could look, brick is 0.47. If we wanted to look at, I mean, there's some ridiculous things in here like chalk. Concrete would be something we'd be interested in. We're looking for the thermal conductivity in a decimal. So this link is in here for if we don't know, and a lot of this stuff is going to be pretty standard. You're going to not know it at first, and then you're going to learn that a wall is made of 2x4s or 2x6s, and you know, some plywood and some drywall and some pink insulation or something similar. You're going to learn that they're mostly made up of the same stuff. Now I did want to point out like this. This is a little bit small. I don't know if I can zoom this in. Look at a diamond's thermal conductivity. Do you see that? Does anybody know what that means? So what we're talking about is how well do these materials conduct heat? The bigger the number, the more conductive it is. So when you look at a diamond, if you didn't know, and a diamond is like a crystal, that is the thermal mass that is, it can hold energy like nothing you can believe. Too bad diamonds are expensive, but diamonds have a real cool ability to hold energy. So a lot of the weird things you hear about crystals and stuff, they come from the idea that they have these high thermal conductivity, thermal mass properties to them. But we can find anything in here that we want, like fiberglass is thermal conductivity. We want to look up wood, you know, granite. We've got to find all of those numbers and dig through them. So that's what that link is there for. So let's back up and recognize there's our thermal conductivity. When we're asked about where to find that, there it is. Another really nice link that I want us to have is this one here that covers types of insulation. I like this insulation link because it shows you a bunch of different types of insulation with pictures. So things that you've never seen before. you can scroll through this pretty quick and see a variety. So what does asbestos look like as insulation? There's a picture. Balsa wood insulation. That seems odd, doesn't it? Different kinds of insulation. You wouldn't even think of brick infill insulation. Stuff I don't even know what it is. Bubble insulation. Cotton insulation. So any type of insulation that you could possibly think of, you could find it, and you could also find the R value of it here based on how thick it is. Foam. Foam is a new type of insulation that they're using more and more. Foam and attics in between. And then we've got fiberglass right there. This is mainly just a reference to help you find certain types of insulation and look into them a little bit deeper. Okay, let's close that one out. So we've got a reference for types of insulation. We've got a reference for thermal conductivity if we have to do a decimal, which you guys shouldn't really have to do that. That's in there just so you know if you wanted to see it, and when we talk about it, what it is. This reference right here is just our climate zone energy map. So if you're trying to figure out what is the recommended insulation that I'm supposed to have in my house for an R value, you can see that, well, in Indiana where we live right in this range of 5. And then you can click down here and look at zone 5 to 8. So uninsulated attic, we want to put in R49 to R60. Existing 3 to 4 inches. So you've got some recommendations if you want to have an ENRG star rated house. Generally, we're going to have about 18 inches of insulation inside our home, and it's just going to depend on the type of insulation that you need. So that's a link on ENRG star rating homes and the zones that you live in, to try to get your house to be as energy efficient as possible. There's also a simple reference calculator, as you can see if you click on here and you've got a window and you're trying to change the windows, you know what the U value is of the window. So if the U value is 1, then you can just click this and you see the R value is 1 there. So they're inverse of each other, but if the U value is like 2, well, that didn't work. I'd have to reset that. Anyway, that's just one calculator, but you can find these calculators all over the internet. You don't need to worry about it too much. Just Google R value to U factor calculator and find one that you like to use. Now, before we get into the text, the last thing is this link here called the diminishing returns of adding more insulation. So this is a unique little link here that has some calculations in it. We're not really concerned about that. Let's see here. Yeah, what we want to look at is basically this picture right here. So what happens is if you only have like R2 insulation, or your R value is R2, then you're losing so many millions of BTUs through your wall. If you upgrade R2 to R4, we see it just cuts it in half immensely. So you see that that makes sense. And then if we go to R6, we're losing half as much heat as we were before, and so forth and so forth. But what you start to notice is once you start to get up here into the high R, after about R20, you don't see a whole lot of difference. So if you're trying to invest a lot of money in insulation, what you have to recognize is there's a diminishing return of adding more insulation. At some point, you have enough, and you're not going to notice much of the difference of the insulation if you put in thicker insulation. Not as dramatically as if you're living in a house that has like R6, and you go from R6 to R22. Oh, huge difference, right? But R22 to R30, not much of a difference is what we see there. Okay, any questions or comments? Okay, see, I've got Tyron and Steven here. Go back to attendance and grab you guys. Okay, so if there's no questions, then let's go ahead and start looking at our text here. So what we're trying to do is we're trying to calculate the total thermal envelope of a building. And we need to understand how to estimate a thermal load. A lot of that we've already discussed, but we've got two types of heat loss. We got conduction heat loss, which is going to be related to just what type of walls do we have. Then we got air infiltration heat loss, which comes across as all those cracks around your windows and doors of cold air or hot air coming in when you don't want it to. And we're going to use software to work on some of this. So there's some stuff that is toward the end of this chapter where it talks about the degree days and what that means. So I don't know why they bring it up so early. So what we're first going to try to learn how to do is calculate the design heating load of a building and estimate the rate at which a building loses heat during a near minimum outdoor temperature. So in other words, you want to try to figure out how cold or how hot it gets and see what the extreme is. So if it gets down to -5 where you live sometimes, then you need to do a calculation of when the house is -5 or the building is -5, how many BTUs an hour am I losing? Because if I do not have a furnace or some type of system to replace those BTUs I'm losing, then I'm going to get cold and my house is going to get cold and it'll get down to 60 or worse, and I won't be able to do anything about it because the design heating load of my building is incorrect. So there are several things that can make the building's design heating load change. So you've got imperfect installation of insulation materials. We have the variability in R values. So if you got wood walls versus walls that are made up of fiberglass, there are two different types of materials with two different R values. Air leakage into the building, all those effects of wind or the overall construction quality really of the building. Second, the heating load is a rate of heat from the building to the outside air. That's how we do it. So the author goes on and says, it is often misstated, even among heating professionals, as the number of BTUs rather than the rate of flow in BTUs per hour. So we're looking at the rate of flow of BTUs per hour that we're losing. Okay. Let's move on down to the section. Why bother with heat load calculations? Well, the reason why we bother with these heat load calculations are just because it's very difficult for us to understand how much heat we're losing. And we can end up as energy technicians estimating the heat loss being too low, and then the building will be too cold, or overestimating our heating loads, and we have a very expensive, oversized system. And if we're going to add anything like a solar or wind or any type of renewables to the home, we need to know how much energy we're losing in order for us to supplement that. And furthermore, if we can discover that we're losing an enormous amount of energy through one area and we can make a change, it can make a huge difference on the cost of what we want to ultimately do if we're building, say, a smarter home. The first section that they get into is talking about the conduction of heat losses. So conduction is the process by which heat moves through a solid material whenever a temperature difference exists across the material. The rate of conduction, heat transfer, depends on the thermal conductivity of the material as well as the temperature difference across it. So what we're talking about is, if we're looking at this picture, what is the temperature inside versus the temperature outside? So there's one difference that determines the conduction heat losses. How fast do we lose heat through this wall? Well, what is the temperature difference from inside and outside? Then we have to ask ourselves, what is the thermal conductivity of the material? Well, the thermal conductivity of the material, we can find that number K when we go to that one page. So they've got thermal conductivity of 0.1 here. We'll see here what it is. And that thickness of the wall is also directly proportional to your conduction heat losses. So we get this formula here that looks gosh awful, I know, but it's going to be something that we have to learn how to use. And honestly, it's not that bad. It's not, because we kind of stick with this formula. We learn how to use this formula and we apply it in a couple different ways, and we can find out how to do this. So Q equals the rate of heat transfer through a material. K equals the thermal conductivity of the material. So that's where we got to look it up on that chart, that reference chart that we looked at. And our X is the thickness of the material and the direction of the heat flow. And our T is the temperature difference across the material in Fahrenheit. And A is the area. So what they have is a 6-inch thick panel. So what that means is this wall is 6 inches thick, solid wood. I'm not sure what kind of wood it is, but you can look it up. And when they looked it up, K was 0.1. You guys with me so far? Hopefully you're not too confused. Like I said, it might take a couple times for you to go through this, but we have to do a little math sometimes. That's part of it. Determine the rate of conduction heat transfer through a 6-inch thick panel shown. So they take the measurements where we have K, and they take the 0.1, put it up there at the top, and then we have X, which means it's half a foot wide because it's 6 inches wide. So we put that down at the bottom. And the total surface area is 200 square feet. So that's going to be something like 10 by 20. So they take the area, 200, then the temperature differential right there, 70 minus 10. So what they've just done there is exactly what we're going to learn how to do. This is a simple version of what we're trying to do. The walls that we have, unfortunately, are going to have an R value related to it. So how thick the wall is one thing, but do we have also foam insulation and plywood? When we do that, we simply add them together. So we can see when we do this calculation, we end up with a thermal conductivity of 0.1 divided by half 6 inches of foot wood paneling. And we end up seeing that we're losing 2,400 BTUs an hour. That's the rate of flow of BTUs an hour when it is 10 degrees outside through this wall. So ultimately, that means we need to make sure that when we build our house, if 10 is as low as the temperature it ever gets, then our furnace has to be able to make at least 2,400 BTUs an hour to get to replace that wall, which that won't be enough because we don't live with just one wall. We have to calculate every wall. So as you can see, every wall can be a little different and the numbers will be different. And then you add that all up and then you've got the total house. Okay. Questions so far? I'm going to assume it's just really overwhelming most of the time when we go through this lesson if you don't have questions, and I understand that. On Wednesday, we'll have a little bit easier time going through this when we talk about it again, and you get to do some application. So thermal resistance of a material. So an object's thermal resistance, which is what is called the R value. Thermal resistance is the R value. Can be defined as its thickness and the direction of heat flow divided by its thermal conductivity. So we can find the R value of anything if we know how thick the material is and we know the thermal conductivity, its thickness divided by thermal conductivity. So the greater the thermal resistance of an object, the slower heat passes through it when a given temperature differential is maintained across it. So as it's getting colder outside, it depends on what the thermal resistance or R value is of our wall. So this formula here is basically the same formula if we scroll back up as this one that we're looking at earlier. But now we're simplifying it a little bit. Instead of having the thermal conductivity divided by the thickness of the material, we just have the R value. So if we already know the R value, we can find the R value I take thickness divided by thermal conductivity of any material. And then we can supplement that R value into the formula in this form, where now we're just taking the area divided by the R value and multiplying that by the temperature differential. So here, I guess this, you got your solid wood. So I was wrong. That first one, I'm not sure what that is. They didn't tell us. It's just thermal conductivity of material. It's at a 0.1 there. They never told us what it was. But on the next one, it looks like the same stuff. So it must be wood. So the R value of wood is 6, because honestly, the R value of wood is about 1 for 1 inch. So if you were to go to your thermal conductivity page and look up wood, you should see for every inch of wood, you're going to get 1 R value. So if you got 6 inches and that's all you have for your wall, then your R value is 6. And that's kind of what I have going on in my house, which is terrible. I only have about R6 in my walls. One of the things I like to mention about R values and wood versus, say, like a cabin versus, say, a house that is made with framing and fiberglass insulation, is that there's a difference in what we call thermal mass. So thermal mass is something that can hold heat for a long time. So does anybody know? Let me ask a question. I haven't asked a question for a while. Does anybody know if you have a thermal mass such as wood versus pink insulation, which one is a better thermal mass, wood or pink insulation? Fiberglass. No, nobody knows. Okay. Well, what is a thermal mass? Can anybody think of a thermal mass and how you would define it? What about water? Does water hold heat?
Yeah.
There we go. Now we got your juices flowing. Yeah, like a hot tub. So I can heat the water up and then it'll stay warm for a while. It's a thermal mass. What about sand? Is sand a thermal mass?
Yeah.
Yeah. What happens when you take, say, you're on the beach and you take your feet or your hand and you stick it maybe a foot down into the sand? Is it hot or cold?
Cold.
It is, isn't it? And that's because it holds that cold in. It's a thermal mass. You go so far. The top part of the sand is warm, real warm. But you just go a little bit down into the sand. So it's a thermal mass. It can hold heat. What else? What about wood? Is wood a thermal mass? Can wood hold heat? Could you make wood warm and it stay warm? I mean, we do burn it, don't we?
Yes.
So it is a thermal mass. So concrete, what about concrete? Does concrete hold the cold or hold the heat?
Yes.
Yeah, it does, doesn't it? So one of the things that I just want you to recognize is some materials have really poor R value ratings, like wood. You have a wood wall that's 6 inches wide. Its R value is only 6. That doesn't sound as good as pink insulation that has an R value of, say, 25, right? And the truth is, it's not as good. R25 pink insulation is pretty amazing on the amount of heat that it can hold. But it does have a problem. Some of this type of insulation that doesn't really count as a thermal mass. So what that means is if you want the heat, you want something that can hold the heat. So if we're talking about building a smart home, a wall, a concrete wall facing the sun can heat up. But if you had a wall filled with pink insulation, it won't really heat up and hold the heat. It might feel warm, but as soon as the sun goes away, it won't take very long for that wall to get cold again. Whereas if the concrete or you've got a wood, a really thick wood wall, thin wood wall is only going to do so much. But a really thick timber wall and the sun is shining on it, that wall can really actually hold heat for several hours. That'll help. But, it's still only going to help so much, because once things start getting cold, having the heat held into the losing the heat is really what we're concerned with. So I just want to point out what the difference is when we're talking about R values, and we think about that, like concrete. They make schools out of concrete walls, and they don't have pink insulation in all of those walls. The walls are made of concrete and brick, and there may be some polyurethane or something along that lines, but concrete is a good thermal mass. That's one reason. Okay, so let's move on from that. So what we have is a formula here. Let's just do this one because it's easy. We have 6 inches thick of this wall. We have an R value of 6. So now we can put that into this formula here. When we do that, we end up having 200, which is the area, divided by the R value of 6. So that makes this formula a little easier. And that means that we're losing 2,000 BTUs an hour through this wall by having our R value. So it's all going to depend on how or what that R value is. Okay, so the thicker the material, the more R value we should see. Let's blow this up a little bit here. So when we get into the next situation, we're going to be looking at walls that have, say, the same square surface area, and heat is flowing through the wall, but we're made up of different materials. So we can have a material 1 that would have an R value of 11. Another material could be wood, plywood, that could have an R value of 2. We can have some foam put in there that can have an R value of 5. We have drywall. What we do is we take all of those R values and we add them up. So if we have a wall that's made up of different R values, we're going to take that 11, that 2, that 5, that 18, add them all up, and then put them into our little magic formula here so we can determine how many BTUs an hour we're losing through that wall. Now, I wish it were that simple. Is there any questions so far on these basic formulas? Again, I know it's tough looking and I know you don't like it, but in order to be an energy technician, you want to be able to say that you can calculate a building's heat loss, heat gain, or at least you were taught that. And you're looking through some of this stuff. So air film resistances is the next topic that we're going to cover today. So we've been going about an hour already. So I'm going to try to keep going for another hour or so, maybe, and we'll see how we do. So inside air film resistance and outside air film resistance affect the rate of heat transfer. So if we scroll down, we start to see an example where we have this little blue air film that's outside. So blue is being colder. We know the outside air temperature is 10 degrees Fahrenheit. And so we have to also, with everything we've learned so far, we also have to include the outside air film resistance and the inside air film resistance. So there's a little formula for it. And it really isn't that big of a deal. I mean, 0.68 is pretty much where you're going to stay. This is one based on the winter. There's one that's based on the summer. And you can find that those air film resistances in the notes. So they're going to depend upon what the temperature is outside. And it's going to depend on, on the inside of your house, does the heat flow up the wall? Is the heat blown down the wall? Is the heat blown away from the wall? Do you have registers right along the wall and the heat's blown straight up? Do you have registers at the top of the wall? It's blown straight out. So they'll give you a couple options where the inside air film resistance number might change based upon whether or not your heat is flowing horizontally or vertically up the wall. And outside air film. So you see there's quite a bit of difference in those numbers there. Okay, I'm going to not lose my place, but I want to back out of this and go into our modules. I'm trying to remember what I was going to do now. Oh, our notes here. So let's look at this. We haven't looked at this yet. And I want to show you, this is where you can find some of those values. So when you do your first homework question for assignment 2, you have an example here to help you. You also have it in the textbook. That's that. We have some definitions in here also. If you're like, what does the COP mean? Well, that's energy out divided by energy in. It's a formula that they use when they rate their heat pumps. And you've got your annual fuel utilization efficiency that we'll put with a furnace. You know, generally it's around, 0.80, 0.90. You have to look that up on your individual furnace. This shows you an example on how to do the calculations for one of the homework questions. If you're trying to determine which is the best fuel based on the size of the house, and you already know what the space heating loss is, though. If you don't know that, you can't do this. Thermal resistance of a material. This is just an example of the formula that we just went through. And then it talks about air film resistances. So what these notes are just little examples of things that you want to pay attention to as we've gone through the book. This is really hard to read on my screen, I know, but here we can find R values directly. So if you don't want to type in the thermal conductivity, you can find most of the R values. So insulation, fiberglass bat insulation is about 3.17 per inch. Fiberglass high densities 3.5. Blown cellulose, you can find anything here on the different types of insulation. Masonry and concrete, there you can find your R values of concrete. If it's 8-inch concrete, you'll notice again, the R values are low. Concrete has a high thermal mass. You can see your wood, depending on the different type of wood, is going to be around 1 per inch. You also may have flooring or carpet in the walls, or it might be what you want to calculate if you're doing some inside space. You see drywall is about the same as wood, 0.9, almost 1. Then we get into our R values of air films. So when we're looking at those air film resistances that blow up and down the wall, we saw one of them that was given to us. It was 0.68. That means that the vertical surface with horizontal heat flow. So heat flow is flowing horizontally. You use this air film value, 0.68. If for some reason it was a horizontal surface with an upward heat flow, you have to think about what they're saying here to understand which direction. So the surface is horizontal. Which way is the flow? It's going upwards. Okay, so from the ceiling. But in general, you can see you pick these numbers here. The outside air films are going to be based on wind. So 15-mile-an-hour wind is a nice average really to have in your winter condition. That's probably about what we are. 0.17 and then 7.5 for summer. So those are where you find those R value resistances in the notes that we have. And then if we want to find the total R value, we would simply add all of our R values up, including our air film resistance. Okay, we're getting ahead of ourselves. You have a few more things in here on concrete heat losses. Okay. Let's get back to our book. So we were talking about the outside air film resistance, 0.17. That is the number or the values and where we can find those values in our notes. Now, the next section that we're going to look at is the effect of the framing members in the walls. So the total effective R value, we have to consider the wooden framing members that span across a wall. So if you have a frame value that is got generally between 10 and 15% of the framing in the walls, so your wall is usually about, like I say, 10 to 15% wood framing. So they have a formula here for finding that. It's quite complicated looking. It's not too bad, but we're going to move forward a little bit and come back to it. So when we're looking at the framing, this is where they're saying that you know typically wood frame walls will have between 10 and 15% of the wall area solid framing across the insulation cavity. So you can see with the thermal camera, you can generally see the studs where they're at. They're going to be either 16 on center with a wood header or along the floor. They'll have that too. So you've got wood running this way, you've got wood running this way, you've got wood running up and down inside the wall. What I like to tell people is if you can imagine that these studs could slide, if you could slide them all the way down in the wall, they would only fill up the wall space about 10%. So what that means is we can estimate a little bit in most cases, and we've got a well, that's what this formula is for, but there's a better way to do it. So we're working our way to it. Okay. So this is what they do to you. They give you two ways that you have to calculate. You have to calculate your wall cross section between framing, which would be these sections here between framing, and then the wall cross section area at framing. So if you have a 2.6 wood stud there, how many of those studs do you have will determine what the R value is. They also have our inside air film versus outside air film. So when you look at this right here, you see them calculate each one individually. So you would want to do this in a spreadsheet, which is what we use. So we would go to our notes and go, what is the inside air film? 0.68. Okay, I like that one. What is the R value of drywall? 0.45. What is the R value of my fiberglass? That's 5.5 inches thick. It's R19. I've got a little piece of foam sheathing right here, 1 inch of foam on my wall. That gives me another R value of actually 5.5. So foam sheathing can add quite a bit. And then a little bit of wood siding, but you don't see that they have the studs on here. And then the outside air film. They come up with a number of 26.5. And then they do it all over again, where everything is pretty much the same, except they swap the fiberglass with the studs. So now we're doing it with the studs. And since we've got a wood stud that's about 5.5 inches thick, you know, they're saying that that's based off of thermal conductivity of wood, which is almost 1. They may have used 0.9 or something like that. But they've got 5.5 as the R value of a 2.6 wood stud, or they looked it up. Then they take those numbers and they put them in this formula, and that gives them the total R value of the wall, including the framing members. So that's how they do it. So now you first got to determine how many framing members I have, and then how many do I need. You could also cheat and take 10 or 15% off, or drop this number down by 2.6, but you won't be as accurate, you know. So it's around 23, 10% of 15%, 10 to 15% of this is what we're ending up with a loss of. So now your total wall R value is 22.9. Let's see here. Okay. Questions so far? I know. I know. All right. So we need to figure out how to calculate the foundations a little bit. We're not going to get into that a whole lot more because we're going to be doing slab on grade foundations. But one of the things that you need to learn about is when we have a slab foundation or we're underground, you have these isotherms. The ground helps. It's an insulated barrier. So how much of your house is underground is a different calculation than doing, say, a house on a slab. So it's quite a bit different. But most of the stuff, you could also have a crawl space. We are trying to give you guys an introduction to how to do this because it is pretty hard to do. When we're looking at basements, we have to look at the basement wall and split it into 3 sections when we do that. That's why it makes it a little more difficult. You have an equation 2.5A, equation 2.5B, and an equation 2.5C. I know some of you are going to be interested in how you do a basement, but what we've got to look at is most of our heat loss is going to be really up here. The warmer heat in the basement is going to go through the center of the floor and radiate out and around. You're going to have most of your heat loss right up here at the top of grade or any of the concrete that is exposed at the top of grade. So in this upper strip here, we would use 2.5. Well, what is that? That's this equation here, 2.5A. Now, we're not going to be doing this, so you don't have to necessarily learn this. The other stuff we are going to be attempting to do, but we're not going to be able to do a basement right away. That takes some time. We got to baby step our way there. So it's going to be based off of these 3 formulas here: the upper, the middle, and the lower. So what it is really the first 5 feet. The first 2 feet are the upper. The next 3 feet are the middle, and then whatever's left is the lower. That's what you would use for equation 2.5C. So let's look at an example. That'll help us a little bit. Make sure this is the one. Yeah. Okay. So they want to estimate the heat loss through a 10-inch thick concrete basement wall that is 9 feet deep with 6 inches exposed above grade. The wall is 40 feet long and has 2 inches of extruded polystyrene insulation, that's R11, added to the outside over its full depth. The basement air temperature, the inside air temperature is 70 degrees. The outside air temperature is 10 degrees. Assuming the R value of the 10-inch concrete wall is 1, because remember the R value of concrete is not that great. So we can see our drawing right here. Solution. So for the upper wall, use equation 2.5 to determine the effective R value. then use equation 2.3 to calculate the heat loss. So that goes all the way back to our original formula, that 2.3 one with the, this one right here is what they're talking about. So if we have 2 inches of polystyrene insulation at R11 and our 10-inch concrete wall has an R value of 1, you can add those two together. That gives you our total R value of 12. We calculate our square footage by looking at just how much 2.5 feet. And then we plug it into our formula here. And we can determine how many BTUs an hour we lose for that section, the first 2.5 feet. For the middle wall strip, we have to use equation 2.5b. So if you remember, that equation looked like this. It had 7.9 plus 1.12. So then we've got to add our insulation to it. So our insulation is 11. So 7.9, and then we multiply that by 11, we get 20.2 for our second part of the wall. And we got to plug that R value into our formula that we've learned how to do already. And we see that we lose 356 BTUs at that temperature. That's not very much because we're underground. Notice the higher we are above ground, closer to grade, the more we're losing. And then for the lower strip of the wall, we use equation 2.5c to calculate the total R value. So that formula was R equals 11.3 plus 1.13. So again, we put our 11 in there, and then we multiply that, add it all up, and we will end up with 23.7. So that section right there is also 3.5 feet. That's what's left over. So we take 40 feet, which is the length of the wall, times 3.5 feet, and we get a square footage of 140. Our temperature differential. And then we can see that we're losing 354. Surprisingly, not a whole lot of difference there between those two. Lastly, to find the total heat loss for this wall in the basement, we had to take 500 plus 356 plus 354 to get our total wall. And that's how we would do a basement wall. We'd have to do each wall that way. And you'd see that you'd lose only 1,200 BTUs when it's only when it's 10 degrees outside, which isn't too bad. You know, that's colder than what it is right now. So it's still a lot, but it's nothing like a normal wall that would lose a lot more because of how a basement is set up and how so much of the heat is absorbed into the ground. So that's the idea behind underground homes, or homes that are all underground. You can see that this method is why they're able to stay warmer. Okay, I know that's not the greatest, but is there any questions so far? Okay, so there's another equation here 2.6a. So we did basements, we've done walls, we've looked at that. And what we end up with is now the option of slab, which is what we're going to go with when we do our project 1. But let's look at this example. So it's pretty much the same formula that we've been doing all along. But we've got to find the effective values. Now, this would be a good time for me to show you our spreadsheet. So when we do this, we're going to have a project that we'll work on together where we're going to try to attempt to apply what we've learned from our e-text reading. So section 2.6. So we're going to be calculating this diagram here, and it's going to be mostly based off the measurements of the walls. We'll go through that together so we can find the total BTUs per hour heat loss when it is -5 degrees out. That's what we want to try to do. When we look at this calculator, I have some examples in here. Let's go ahead and blow that up of how we do this. Make sure that looks right. It does. So you're going to need to download this calculator when we get into this. So one of the reasons I want to show you this is because I don't want you to start to get any more like, oh my gosh, I don't want to do this. I hate this. Because I understand that it's complicated. What we have to do is plug in these numbers. And most of this stuff is going to populate on its own. And we'll end up with a number at the end of it. So we're going to have this given to us. And the space 1 that we have, what I've done is I've taken and given you some R value information. R value for all the windows is 3. What does that mean? That means when you go under this section of windows, you put an R value of 3. The unit R value for an exterior door is an R5. So what that means is when you come over here to exposed doors, you're going to put in an R value of 5. The area, you're not going to calculate up here at all. So the exposed wall, that's where it gets tricky. This is where you're going to be given some information, which comes from the text. So this actually calculates when you're gonna have to open it up in Excel in a spreadsheet to do it. And like I said, I would wait until Wednesday to even really look at this thing. But what I want you to see is this is how we're going to do this. Inside the spreadsheet, you'll be able to populate between framing and at framing. So all we have to do is put in these numbers, which I'm going to have that done for you just to make it easy for you, because it's coming straight out of the text. And the example, this question comes from the book. So it's really just what we've already looked at, where we typed in our inside air film, between framing versus at framing. So it's pretty much all the same, except the stud cavity. We have our value of 21 for our pink insulation, but at framing, we have 5.5 with our frames. We also have some plywood sheathing. Vinyl siding has no R value, really. I guess it depends on what you're looking at, but not really. And the outside air film. Take all that and you got to plug it into that effective R value formula that we looked at earlier that we kind of breezed over because we're not going to be doing it, because it's going to calculate your R value automatically right here. 18.9. This one is for the ceilings. So you have to do the walls and the ceilings separately in order to do this. Again, we're going to use what the textbook has. So we're going to pick an example, and this is it. This is our example. What you're going to have to do is measure the walls, measure the windows, and do a little bit of thinking and put it in decimal. So if we have the length of our gross exterior wall, we've got to look at a wall like this, where the height of the wall is given. Not everything is given though. Height of the wall is 8 feet. Our window heights are 4 feet. We have our design temperature, outdoor and indoor. We haven't got to air infiltration yet. We'll have to talk about that later. But we're simply going to take the width, which this right here, 7 feet, right? And you got to take 9 inches. In order to get it in the decimal, you got to divide it by 12. So 9 inches is going to be 7.75. You can see over here, we did the same thing on the length, but what we got to notice is there is only part. We got a window here, and we got what looks like a sliding window here, sliding doors. We're going to call it a window, considering that we've already got this done. So if you take 5 divided by 12, 9 divided by 12, add that up to 4 and 3, you're going to end up with 8.17 in your length. And that's another reason why I want to sit down with you, make sure you understand how to do that. When you know and you go into the building and all you really have to do is measure the wall and use this calculator, this gets a lot easier. So now we go ahead and plug in the length of our wall, and we get a value of 127.4. What we're going to notice is these values are going to be used to automatically populate these numbers at the top. So you can see the window area. We calculate the number of windows, and we see that we are at 39.32 for an R value there. And that number came right from here from our measurements. That means that we're losing 983 BTUs per hour. That's the rate of flow through our windows on that wall in this space. Same thing with this exposed wall here. On all of our exposed walls in this space. This gets all added up, and it'll give us our total number here, 3,409 BTUs that we're losing. Any questions on that spreadsheet? I know we need to look at that together, but in this form here, it's not going to do nothing. You got to download it.
So is it for the room temperatures, is it gonna be covering like
Good
what
question.
the
Right
room
there.
temperature itself is?
Yeah, so,
Would
When
the wall also have its own ambient temperature compared to the inside and outside?
yeah, well, what you would type in is and that's being taken care of. The inside air film is kind of that ambient temperature of that wall. That's what that's what we're looking at. It's complicated, I know. And our outside. So the inside of the wall versus the outside of the wall. So if I were to take this calculator and I were to type in 70 here and 70 here, then I would be at a thermal equilibrium. So when we're looking at the temperature, it's only when I put in -5 right here in this calculator that this is going to change and show me how many BTUs an hour I'm losing. Okay. Let me see where we're at in our textbook. Any other questions on anything or on the calculator? You can get in there and play with it. You know, if you mess it up, you can always re-download it and it'll be fresh. If you mess up, you gotta be careful with some of the formulas when you're clicking around and deleting in your boxes that you don't delete something out. Yeah, okay. Oop, I'm gonna have to go back. Okay. Yeah, this is why we're getting close to being about where I probably want to stop here soon. I want to see where we're at so you can absorb some of this information. I know it's just too much. Textbook's very hard. This is a enormous textbook. We wouldn't want to buy it. It's like 1,000 pages long. It's just really expensive, but it's the best book I could find that actually teaches you how to do this stuff really well. Okay, so we got through all of that. We did look at basements and we were on slabs. So I think, let me scroll ahead a little bit more. So we talk about slabs on grade, floors. Yep. We got to talk about coefficient a little bit there. Different types of soil we still got to talk about. Then we get into heat loss through windows, doors, and skylights, which is U factor. Right there's your U factor, R equals 1 divided by U. And then it gets into infiltration heat loss, which is energy auditing, which is not, we're not really wanting to jump into that just yet. Because that gets into blower door stuff. So yeah, I think that's probably good for today. It'll get you started on your homework. I'm going to extend this homework to be Wednesday, not January 31st, just because this is such a big lesson. Because we're going to come right out of these calculations, we're going to go into energy auditing and into blower door testing. We have a blower door. We're going to have to get that set up in the house. Just kind of learn basics on how to do that. That's fun. but yeah, I think this stuff's gonna just get a little too much for one whole lesson. So, yep. We've already looked at that a little bit. But I think what I want to do is let you kind of read through this and absorb some of the stuff that you got to. You could get started on your homework. You have, let's go look at that. So let's click on modules. So like I said, this is for week 2, which week 2 starts actually on Wednesday. So we're a little bit ahead of ourselves. That's good. So we can try to absorb some of this information, not all at once. Now it gives us time to kind of go through this. Now we want to look at our homework assignment. Your homework assignment is pretty easy. It's just going to be a lot of true and false questions for the most part on some of the information that you went through in the text. So none of those calculations that we went through today. That's kind of hard. But I mean, there's still stuff in there that we talked about, like air film resistance, knowing that advantage of using software. I mean, you just saw what the advantage of the software is going to be, because we're going to be able to change the temperature any way we want. So if we want to see what it's like at 70, we want to see what it's like at -10, -20. And once we do our building, our room, you know, you could do your own house. I did mine, and I discovered a lot of stuff that I did not know about my house and where I was losing all of my heat. I mean, I kind of knew, but I didn't know how bad it was. And so now I know, and I know I got to actually do something about it, or my heating bill is going to go through the roof, literally. So that's just part of being able to do these calculations, or at least have an understanding of what it is that's going on, or how would you even do that, you know, instead of just not knowing. So I wanted to scroll down. So there are a couple questions that are further into the chapter, like blower doors. So you're not quite there yet. So that's why I'm going to change the due date on this. That makes sure I can get through this stuff with you before you have to turn this in. But you have 3 attempts on it. You can see the answers. It's not too bad. Okay, we need to get you to answer some questions. This is where you do that one calculation, cost benefit ratio calculation. That's from the first chapter that we did, the residential basics. And then this next one here is the same thing, where you got to calculate that too. So, you know, you're stepping back. You really just got to pick which one is the one. So you'd want to do this on a piece of notebook paper first. Just write it down and type out your answers for each one, and then go back and answer these all at one time, just to show that you can do basic math. And I have to do certain amount of math. It's required by APME, and I try to pick things that are relevant and not extremely difficult to do. And I try to help you as well. So when we get into things like this spreadsheet with all this math, what do you really do with that? Well, I think we can use it and in a really cool way now that we have the spreadsheet there for us to use. And then you can take it from there if you want to add more and learn more. But that's the homework. Let's see here. I think that's pretty much it for now. Don't think we want to do too much more. So let your brain rest from that for a little bit. And then you're going to want to try to read through that text a little bit and get a little bit better idea of what's going on, and look at the calculator. I know you're going to feel lost, but eventually we're going to be able to take what we've learned in this chapter, all those calculations, use our thermal envelope calculator, which will be easy to use once we practiced it, and actually calculate the thermal load of our energy center. So each one of us will be able to go into a real room look at the room, take the measurements, do the real calculations, and then we'll move on to some energy auditing as part of that. So we'll be able to know your space and your dimensions like you should. And you won't have to just not know. You'll know how to do it. Okay. So I apologize for how tough this lesson is. I know it's tough and I know it's not fun, but I'm right there with you. I'll help you get through it. And Wednesday, we'll take a look at it and it should come together a lot better on Wednesday. And then when we start doing application, the stuff will start sticking in our head and we'll kind of know more of what we're talking about and we'll be able to reference things. Are there any questions for me before I let you guys go? Okay, well, that puts us at about 2 hours and 40 minutes or so. So I think we'll call that good for today. And we'll pick up on Wednesday and Monday some of this information. And I will see you guys later. Tomorrow night's class, if you're in tomorrow's night's class, it's at 5 p.m. So we'll be meeting virtually for that course, just so you know. Okay, well, if you don't have anything, I'll see you guys later. Have a good rest of your afternoon.
Thanks,
All right.
John.
Thanks,
Yep.
John.
Have a good day.
Thank you.